announcement. I wrote up some lecture for my mini course that starts tomorrow, and they're out there. Excited about it. Okay, so our first speaker in the afternoon is Tobias Ekholm, and he'll be telling us about exact Lagrangian convergence with the single double points.
Thank you. First, can you hear me? Okay. So, it's of course a great pleasure to be back. So I'll prepare some slides for this. So first, it should be said that whatever I say here is about don't work with Ivan. And I will start out by just giving a very basic background, being known to all of you, and then fall asleep for the first part of the talk. And then I'll state the results that I'm going to talk about, and after that I'm going to try to indicate how the proof goes of these results. So just to start out, we think of a smooth manifold with local coordinates, and then associated with that smooth manifold is a cotangent bundle, and there are some momenta conjugate to the coordinates. So and they are doing symplectic geometry. So there is an action form, which is the form PDQ, and then if you take this derivative, you get the symplectic form of the cotangent bundle. So this is of course well known. Now more explanations of words in the title. So if you have an immersion of a K-manifold into such a cotangent bundle, when is it a manifold? It's called isotropic if restriction of this symplectic form to it is 0. And then it can have a gross dimension n, so half of the dimension of symplectic manifold, in which case it's called a Lagrangian. And this will concern exact Lagrangians, and exact Lagrangians are Lagrangians which have the property that if you take the pullback of this primitive of the symplectic form, then you get the closed form, and here you require that it's also exact. So then it's called exact Lagrangian. And the prime example of an exact Lagrangian is the zero section in the cotangent bundle. So of course, it's trivial to find such function, take the function 0. A way of generating other examples in cotangent bundles is by taking a Hamiltonian, time-dependent Hamiltonian. So you take a function of this cotangent bundle, time-dependent one, and then you define Hamiltonian vector field. So it's the omega dual of the differential H, and you use this Hamiltonian vector field to flow the zero section. Then you get some other Lagrangian embedding of the zero section, and it's somehow exact because it's classical mechanics there, that's where the form is preserved. So there is a conjecture from the early days of the subject by Arnold that in fact all embedded exact Lagrangians in the cotangent bundle are obtained this way. And this is known in some cases, so the first few cases, but as far as I know, it's open in general. And we're not going to study that exact question, but we're going to look at the weaker question. This nearby Lagrangian projection in particular contains the statement that if you're an exact Lagrangian in the cotangent bundle, then you should be diffeomorphic to the zero section. So it's formulated slightly differently. We might ask whether the symplectic geometry of the cotangent bundle actually feels the smooth topology of the underlying manifold. And the basic, before we come to smooth topology, we have some sort of homotopy theoretic invariants. And And there are ways of getting at those via versions of fluorine homology, let's say. So I don't want to be very precise here, but I mentioned a few names. So there's Foucault, Simon Smith, and there's Jose and Krag, and there are many other contributions to this. But the outcome, if you add all these papers, is that if you're an exact Lagrangian inside a cotangent bundle, then you're in fact homotopy equivalent to the zero station. So now smooth topology goes, of course, beyond homotopy equivalence, and we are going to try to get at the other parts of this thing. Okay. And the techniques that we're going to use is maybe not so surprising for considering a workshop and so on, but we are going to use sort of homomorphic curves, and as you all know, they are pioneered by Ekholm, I'm sure. And so, to give one example of what we are going to do is somehow the starting point for this is the rigidity theorem of Malden's problem, this original paper that says that there are actually no exact Lagrangian embeddings of a closed manifold into complex space, which we view as the cotangent bundle of HUN-REN. And this theorem is particularly simple in dimension 1. So, but in fact, somehow even the one-dimensional case contains somehow the proof that we are going to give this theorem and some other theorems. It's a very much generalization of this simple proof. So, if you think about it, you have this curve gamma, which is supposed to be exactly Lagrangian embedding or immersion in this case. So then you can compute the area that it bounds by integrating the action form with negative sign. But if it's exact, then this, you can see that this is 0. And so, particularly in dimension 1, if you recurve on the plane, and you have no intersection points, you bound positive area, and so you cannot be injected. And so now I'm going to continue. So I'll discuss a more fancy version of this theorem, high dimensional, and so on later. But before going into proofs at all, I'd like to say a few more words about the background. And so I'm going to tell you something about exotic spheres, and that's also unusual situation in talking about exotic spheres, because the person who taught me everything I know about exotic spheres is someone in the audience. So I have to kind of try to keep saying correct things here. Okay, so first there is the sort of continuous Poincare conjecture, which asks whether if you have a manifold that's homotopy equivalent to an n-sphere, is it then homomorphic to the sphere? And this is, the answer is yes. In high dimensions it was easier, so it's way than in pair 1. But the C-infinite Poincare conjecture is not equally true. So there are smooth manifolds that are homotopy equivalent to the n-sphere, but they're not diffeomorphic to it. And the first few somehow numbers in this list look as follows. So first, for a while, 1, 2, 3, there's only 1. But then in dimension 4, we don't know. So this is a smooth 4-dimensional conjecture open. Dimension 5, 6, it's 5, and then comes the sort of first dimension we never found exotic spheres where there are 28 different structures. And then 2, 8, 6, 992, and somehow those guys the first 16 number of, in the first 16 dimensions, this is the number of exotic spheres. And you see that in dimensions on the form 4k minus 1, so 7, 11, and 15, there are much more than in the other dimensions. And that can be explained by how we actually find this exotic sphere. So we sort of peek into the next dimension, and one could say that the signatures of 4J manifolds are responsible for the many homotopy spheres spheres in one dimension below. So now, in this talk, I'll focus on even-dimensional spheres, and there the classification of standard, the characterization of the standard sphere is a little bit simpler, and because it's the only sphere that bounds a parallelizable, stably parallelizable 2K plus 1 manifold, where we say that the manifold is stably parallelizable if when you add the trivial bundle to the standard bundle, you can somehow find a frame. Okay. So the main result that I'm going to talk about is the following theorem. So we start with any closed orientable 2K manifold, so it's even, and here K is bigger than 2, so we're not in dimension 4, there's nothing spectacular. So we're in high dimensions. And we require that the order characteristic of this manifold is not minus 2. So in particular, homotopy spheres or okay, they have order characteristic 2. And if it has an exact Lagrangian immersion into a complex 2K space, which has exactly one transverse double point, no other self-intersection, so that's the figure 8 that we saw before, then in fact, the manifold is diffeomorphic to the standard 2K sphere. So there's only the standard sphere that has such immersion. And that means that somehow this Lagrangian, the symplectic topology, the symplectic topology feels something about this new structure. In general, as those of you probably heard who were here last week, that there's an H principle for Lagrangian immersions. And so that means that any homotopy 2K sphere has exact immersions into C2K, but this theorem says that they have more than one double point. And it seems, well, first I should say that it's interesting to compare this to somehow Morse theory. So the double points of Lagrangians are oftentimes compared to critical points of Morse functions because if you take the zero section and shift it off by a function, then intersection points correspond to critical points of this function. And so any exotic sphere has a Morse function point with just two critical points, one maximum and one minimum, because we glue them together. So in some sense, this says that this Lagrangian world is a little bit more sensitive to smooth topology than Morse theory, perhaps. It should also be mentioned that Abusai proved a very similar result using actually similar methods, conceptually very similar, technically a little bit different, but maybe just a question where you turn to when you have difficulties if you're sort of algebraically applying it in a few months. So he proved that in some other dimensions, so 4K plus 1, that if you're exactly one use of manifold of the tangent bundle, then we bundle parallelizable manifold. And most often there are two such exotic spheres, except in some exceptional dimensions. So the result about double points can also be, as a corollary, we get the following thing, which is more in line with the Mohammed group. So if you take the manifold S1 times Sn minus 1, so then it's known also, it's known that if you're a manifold that is homomorphic to this manifold, then you're diffeomorphic to connect sum of it and the homotopy sphere. And they're so the characterization of these smooth structures of this manifold. And we get the following result, that if the dimension of this manifold is 8K, then in fact the cotangent bundles of P connect sub sigma and P are symplectomorphic if and only if they are different let me make some comments about, I'll go back to the theorem. You see, there is this assumption that the Euler characteristic is not equal to -2, and one might ask whether this is really necessary and so on. And in fact, as I'll tell you in a few minutes, it's not too hard to see that if you have an immersion with one double point, then your Euler characteristic is either plus or -2, so much of it is just ruled out by very basically wrinkling or something. But -2 cannot be ruled out, and in fact it turns out that this is a very necessary condition. So and the starting point for that was a result that somehow was a little bit forgotten, but Subhashini constructed a Lagrangian immersion of a genus 2 surface, which has Euler characteristic -2, with one double point. And he did this under the direction of Odenberg, who was his thesis advisor. We managed to generalize this, so Subhashini's construction is not immediate, but using the same type of arguments, you can do something similar in higher dimensions. So you can find an exact immersion of the connect sum of P with P. So remember, P was S1 times Sn minus 1, so it's a generalization of genus 2 surface. And you can find such a thing with exactly one double point. And this immersion, if you lift it to a Legendre, is a loose Legendre. And in fact, using Murphy's H principle, I think you heard about last week. So you can use this that H principle together with this immersion gives the following result: that if your N manifold, which contains this Q, the genus 2 surface of higher dimensions, as a summand, then you can somehow find a Lagrangian immersion with the minimum possible number of double points as predicted by Euler characteristic. So it's really kind of a very crucial assumption, this Euler characteristic. And it should be mentioned that if your Legendre, the Lagrangian, has a Legendre lift, so that I should say something about this Legendre lift. So we're working in Cn, and we have exact immersion. So we can take Cn times R, and on that space, we take the contact form dc minus y dx, and the lift of the exact Lagrangian, which just adds the z coordinate, is a Legendre. And as you may or may not know, but as you will know after many lectures, you can associate a differential gradient algebra to such Legendres, and if that algebra admits an augmentation, which in phenomenological terms correspond to it being non-obstructed, then one can show that the number of double points it has is at least 1/2 of the sum of vector numbers. So this is like Morse inequalities, but with the factor 1/2. So in some sense, the existence of these immersions, Lagrangian immersions with very few double points, are a little bit surprising from point of view of these sort of rigidity theorems, and it's not completely clear. It's clear that it fails, but it's not completely clear how this sort of phenomenological argument fails. Right. So now I want to say a few words about the proof. And the first step of the proof is somehow very simple. So if I just look at the normal bundle of a Lagrangian immersion is equal to a standard bundle, and the Euler characteristic of the normal bundle can be computed by counting median dimensions and number of double points. And in particular, we find that if you have just one double point, you have Euler characteristic plus or minus 2. And then we would like to somehow find some more information about this double point. And when you deal with this de Chambry lift, you can associate a you can see for grading reasons. So it means that if the associated to the double points, which are red points of the de Chambry, is an index, and this DGA is, as the name indicates, graded algebra. Augmentation is a gradient map from it to ground field, which is just C. And so in particular, in this case, you have no generator of degree 1. And that means that it's automatically augmented this DGA. And so I'm saying this to you understand some of these words and then source talking about them. But it doesn't matter so much exactly what it means here. But it means that you can define a linearized version of compact homology, which in this case behaves just like the Fermi homology of two copies of this immersed Lagrange. And there is a duality result which shows that the topology of the Lagrangian is reflected in the linearized compact homology. And that gives you more or less immediately, because now you have just this single homology generator, and so the thing has to be a homology sphere. So basically, in this linearized compact homology, you find all the homology, actually half of the homology of the manifold that is being immersed. And so here there can be only two classes, so it's a homology sphere. And then one can go further and use results of Damian, who studied Fermi homology with, let's say, twisted by some local system. And in that way you can get at the fundamental group, and here, and I'll describe in a minute somehow what the Lagrange surgery is, but using these results you can actually find that the assumptions, so we have homology sphere already, but then we can move on and show this effect as a homology sphere. So these are somehow, I shouldn't say standard, but tools have been worked out before. So let me try to kind of come to the things that we're actually doing. Here we'll use Lagrange surgery. So that is, we will remove the double point. It's not really necessary to do that, but we'll do it anyhow. So that's how we did it in the paper. And what it looks like is the following. So near the double point, except for that is the Lagrange inverse, but near the double point you can straighten the thing so that it looks exactly like HUN-REN and I-REN. And then you remove a small disk around the double point in either one of them, and then you sort of want to run the tube. And in this way, to get the Lagrange, you can think of running the tube as follows. So you can take the sphere and you multiply it by e to the ix. Right? So where you go like this, or you can multiply it by e to the minus ix, or another direction. So topologically, nothing happens. You just add the one handle. So you're making somehow. If you start with the sphere, you're making S1 times S7 minus 1. But Lagrangian, as a Lagrangian embedding, they are different because they differ by the master class of the Lagrange circle. So the master class, say something about, but we'll work with this Lagrangian which has master class equal to 2k. So I'll say something about the master class in a minute, but let me first say something about what happens in odd dimensions, because somehow we're in even dimensions, and odd dimensions also something can be worked out. So I'll jump to these. So using, Fukaya, but anyway, so using work of Fukaya, who is somehow mixing Floer homology and, let's say, string topology, Salon, he shows that in fact if you do this surgery and then you look at the result, then if you have an one-dimensional sphere with one double point, then in fact its DGA also gets orientation. So it cannot be obstructed for homology. And so one can push the argument that I'm going to give slightly different guys to show that such a manifold would also bound state parallelizable manifold. You can show this directly in dimensions, and in some of the old dimensions, it will also bound parallelizable manifold. K minus 1. So this is sort of one direction which we should generalize. And the other thing that one should mention here is this kind of signature. So in dimension 4K minus 1, there is the signature of structure. So here, later on, I will show that we actually bound parallelizable manifold, but in these dimensions, it's not quite enough. And one can now play with this signature and define, turns out, I'll comment on that maybe later, can define the signature invariant, that is an invariant of exact inversions with one double point. And the simplest, at least for the simplest inversion, this is invariant is 0. Maybe for all it is 0, which would be then lead to similar theorem in all dimensions. But before I talk about that, let me back up and say what is the mass of index. So the mass of index is a function. So for we have Lagrange inversion, the mass of index is now a function of its first homology. And if you take a loop inside this manifold, you get the following the tangent planes of the Lagrangian along this loop. You get a loop of Lagrangian planes, and pi1 of the space of Lagrangian planes, or h1, is integers, and so you get a number which is called the mass of index. And here's the description of how to compute it, but it doesn't matter so much. Maybe look at some concrete example later. So the main point that the main tool we will use to prove the theorem is actually studying a moduli space of homomorphic curves. And in this setup, the equation defining homomorphic curves is called the Riemann-Hilbert problem. So, or at least the linearized version. So let me sort of quickly say something about that. So we fix an almost complex structure on Cn. Of course, we could take the standard complex structure if you wish, but it gives more freedom to take any almost complex, more perturbations. And then we take the disk and we look at maps from the disk into Cn with boundaries in a field given loop of a Lagrangian plane. So let's see. So we have defined an operator which is just a sort of Igor operator with a zero return. So now down here, which acts on such functions, satisfying these boundary conditions, and map them into LP functions, or LP's complex antilinear maps of the tangent bundle of the disk into Cn. And such operators, looking like let's call them Cauchy-Riemann operators, they are Fredholm, so they're elliptic, and they have index, which is given by this mass of index. So their index is somehow the ambient dimension plus the mass of index. And so we're in our proof of the theorem, we are going to look at perturbed Cauchy-Riemann equations, and this way of perturbing the Cauchy-Riemann equations is rather classical. It goes back to work of O and Fukaya and others. And so what we're doing is we're doing the following. So we fix some Hamiltonian time dependent on Cn, such that we have our immersion with one double point, such that if you shift time 1, then you shift this Lagrangian off of itself. And then we are going to perturb the Bohr equation with an Hamiltonian term which sort of gradually comes to this Hamiltonian. So we fix a function which is it's a sort of a bound function. It starts out as being 0. It's a one-parameter family of functions indexed by R. And so at 0 it's just a 0 function. And then you grow a little bump, and when this bump reaches height 1, so now let the function go out towards the constant 1. Right? So the bump and going down to 0. And we look at the one form, this function times dt on a strip with coordinates s and t. Right? So s is the long coordinate and t is the 0, 1 coordinate. And we want to identify the strip with the disk with two punctures on the boundary, so we take such a conformal identification, we pull back the form called gamma. And the equation that we are going to study is the equation written up there. So we look at functions from the disk into Cn, taking the boundary into the Lagrangian, and satisfying the following differential equation, which is somehow the Floer version of polymorphic curve. So it's so you take the 0, 1, so the complex antilinear part of the differential plus the Hamiltonian vector field times this cutoff form. Right? So at 0 there is no perturbation, it's just a standard de Boer equation. At infinity you have everywhere this Hamiltonian. So in local coordinates the equation looks like that. So in terms of the strip coordinates s and t. So the first part is just an ordinary de Boer equation, but then comes this cutoff Hamiltonian vector field term. And we write this f or j beta for the space of solutions with boundary conditions. So the boundary maps into L, and L is somehow contour equivalent to S1 times Sn minus 1. So its first homology is corresponding to S1, and we fix a class where the boundary maps into. And remember that the mass of class of this generator was 2K, the mass of index. Right, and then we take the parameterized moduli space, we take the spaces of solutions for all R. And if we, so this is somehow our main object of study, this space of solutions of these equations. We'll say a few words about its properties. So first of all, the main sort of property of the space is that it's the norm of the derivative of solutions to these equations are actually topologically controlled. So it's somehow an area integral plus this Hofford norm-like thing. So our Hamiltonian needs just to shift L off of itself. So this is a finite number, and one can then show that in fact if you take R large enough, so if the support is big enough, you have no solutions to this equation. So if we look back, this is also well-known argument. Just to say the completeness, if you look back, you see that this equation. So one can show that as you go out asymptotically towards either infinity, you actually have to go to a solution to this what's behind J. So you have to converge to some Hamiltonian core. But on the other hand, the energy is supposed to be finite, and that doesn't go so well with that, because if you're a Hamiltonian core, then you go out, you have to derivative all the time. So when you blow up. So if we're large enough for you make it long enough, then otherwise the conversion such solution would have too large energy. So in fact the moduli space, so the space of solutions is empty after some sufficiently big R. And also we can compute, by this Fredholm index, we can actually compute the formal dimension at least of this manifold. And that was given by the Maslow index plus n, and in this case n was 2k, and the Maslow 2k times j for this loop, so you see that the dimension is given like this, where the last one is because we have a parameter problem, so we have this one. So the solution spaces are looking like this, and in fact, just standard transitive arguments from the business. So this will summarize this partial integration with UCT, which is this unique continuation principle or something plus Sortswing theorem, shows that in fact for generic choice of H in complex structure, this is a C1 smooth manifold with a given dimension. So if we look into more detail, we find that this F0 beta, so the ones, the holomorphic or flow holomorphic curves, which represent the zero homotopy class, they're actually forming a 2k plus 1 manifold, and the boundary of that manifold is canonically, so the boundary of course corresponds to one of the boundary components at least. It corresponds to r equals 0, where we have no perturbations, and that's somehow canonically equal to n, because there is a constant solution. So there can be no others if you think about, let me go back. The holomorphic curve equation, just deleting the second part, you find that you have ordinary holomorphic curves, and such curves, if they're non-constant, have area, but removing somehow, but the area of them is obtained by calculating integrating DDQ along the contractible loop, so that's 0. So therefore we have constants only in the beginning, and then something happens. And what happens is controlled by also classical theorems for this sort of normal compactness. And let me just give a small, short description of normal compactness for those who haven't heard it. So what we're doing is we take a sequence of solutions of our problem. So boundary in L and holomorphic, or flow holomorphic. And now, if you look at the sequence of derivatives, that remains bounded. Then, by sort of just standard analysis result, which is serious for the theorem or something like that, we extract a convergent subsequence. So we need to understand what happens if the derivative is not bounded, and if it's not, then we somehow use the conformal invariant to rescale. And we take the little piece where somehow the gradient is the biggest, and we rescale. And if we rescale by the maximum derivative, then we get something with bounded derivative. And the point is that when you do this, you somehow the domain converges to a half plane or a plane, and the map converges to something with derivative 1, so to a non-constant homomorphic curve. So, and note that the limit solves actually not the flow equation, this bubble, but it solves the ordinary equation without the extra term, because the extra term disappears in this case. So in order to understand the limit, we need to understand the space of solutions of the unperturbed equations, and I'll denote that space by nj beta. Again, we have some sort of homotopy class on the boundary, which is in class j beta, and I put the star because there's one point which we have to keep track of. And again, one can show that this somehow can achieve genericity by perturbing almost complex structure, and we get also a manifold of these dimensions, so similar to the other ones, except we have to now subtract automorphisms. Okay, so there's some sort of simple observation that, in fact, there are no truly homomorphic curves with boundary which goes negatively around it, because they will have negative areas, so they cannot exist. So these quantized spaces are empty. So we can now kind of try to understand what's happening. And in fact, the upper part is supposed to indicate the general case in normal compactness. And so what happens in the general case is that you start with your fluoromorphic disks, and from these disks some bubbles grow out. Now, you cannot say that there's one bubble or so on, but you get the bubble tree in general. So when you start this cascading procedure, you get the homomorphic curves, but it could be further bubbles in the story. But each bubble eats something. So this is the picture that you have in mind. You have the fluoromorphic disk somewhere, and from it grows out a lot of homomorphic bubbles. But now in our case, we're in a very special case because our sequence that we're converting, we were studying the moduli space F0 beta. So the fluoromorphic curves with non-homotopic boundary. and then, of course, in the limit, the sum of homology classes of the components is the homology class of what we started with. So in particular, the sum of all the coefficients moving somehow, there should be betas in the box, we know. The sum of these numbers is equal to 0. But because of area reasons, as I just said, all the wrapping of the homomorphic curves, they're actually positive. So it needs just one possibility, namely that there's only one way here to get the sum 0, and that's to have an element in this f minus beta, and attached to it one curve in m beta. So that's all initially what we could imagine in the band boundary like this, but this actually doesn't happen, so it can only bubble into two components, one fluoromorphic and one homomorphic. So what we find is that, at least topologically, the boundary of this moduli space F0 beta is L, where the constant maps at one end, and then, as I deform, I find eventually no solution, so the other boundary would look like a fiber product of solutions in class minus beta and this homomorphic curve. So that's exactly what these pictures indicate, right? So you have this fiber product over evaluation map, and the curves sit together at this point. Okay. Now, this in fact is sufficient to give the proof of Grombo's theorem that I mentioned in the beginning. So assume now this RL is exact. So then if you have no bubbling at all, then what would happen? Well, you have your deformed moduli space, this F0 beta, and if there is no bubbling, then it will be a closed manifold. But on the other hand, you have a degree 1 map from the boundary of this manifold into L. And that doesn't go so well with this. This evaluation map extends, so the degree would have to be 0. So therefore there has to be bubbling, and that means that there would have to be a double. Otherwise, it's very too hard.
Sir,
Yes.
what do you mean by boundary of F0? More precise.
Right. So here, in this case, I would say that this is somehow the simplest way to say this is that you have a compactification, right? It looks like this. But the honest way, the way that I'm actually going to use in the theorem, I would have to prove that this is true in C0 sets. That F0 beta is somehow, it's a smooth manifold with smooth structure. And I would have to add on a column neighborhood of this to create the compactification. So I would want to have this as a C1 statement with, so somehow on the open part of F0 beta, the smooth structure is given by the equation. On the broken thing, it's also has some smooth structure, but I need a gluing theorem that actually makes the boundary C1 smooth. That's where most of the work in the paper actually goes into proving that. So, but I'll say a few more words. But for this, it's somehow fairly weak. For this global thing, a very weak version of this solution. But you just need to say that there is a boundary, and then you're done. So if they're both smooth, you certainly get a smooth boundary. So indeed, as your questions indicate, so the strategy here is to look at the moduli space and then more carefully study the boundary and see what's going on. So at least we can understand this somehow, the broken solutions, because if we think about this f minus beta, then by the dimension formula, this is just it's a compact one manifold, and so it's a bunch of circles, and we can of course extend this. One can check somehow what's the evaluation map from this thing into the manifold to a solid torus, and then we would like to, which I call T, so union of solid torus, and then we would like to take the fiber product of this torus, the solid torus with the moduli space, and use that as a plug to complete the manifold. Right? So initially we're getting this F0 beta, and we artificially add on some other pieces, which makes it a closed manifold. And now for us, it's crucial to have a C1 structure on that manifold. Right? And that involves some serious gluing analysis, in the sense that you need to take these broken solutions and you apply somehow Floer gluing to get them into the moduli space, but you need to do it slightly more carefully than what you normally do. So in particular, the way we do it, since you asked the question, so the way we do this is somehow we try to fix gauge in some way. So we just cover the moduli space by fixed gauge states. And we get the family of shorts and then show that this is an atlas. So that didn't matter so much how we fixed these things. And then we prove the gluing with this fixed data. So then it's more like a standard Newtonish iteration gluing. But what it involves fixing this gauge is somehow looking at so we have this homomorphic curve with one mark point, and what can the homomorphic curve look like near this point? And in fact, if the derivative is non-zero, it's kind of pretty straightforward to find two nearby points with markers on, but derivative can sometimes be zero. So we develop some theory which works a little bit with the jet condition. So instead, so from technical point of view, this is a little bit less absurd. But anyway, so we make the Riemann real analytic, and then we have a lot of local solutions, which are just kind of polynomials. So we replace the homomorphic curve near the mark point where we need to put the function by some kind of standard piece, and then control all the coordinate changes. So it's some sort of serious analysis that has to be done, but it's given this idea, it's a certain more or less standard. So we find a color here on the boundary, and so we glue them together and we get this movement. So now we want to finish, and we want to prove that this W that we created in fact is stably parallelizable. If it is, then we're done. So we know that L is the boundary of stably parallelizable manifold, so it's a standard dimension. And this is somehow is a strange way of proving it. So we're borrowing certainly from Mohammed. And the point is that somehow it turns out, together with homotopy theory, it's somehow enough to prove that this is so for a standard, in a standard example. So we have here some of the model immersion, and we give it in this, presented in this way, so it's a sort of spirit of Lefschetz vibration. So this is a standard immersion of the sphere with one modality point, or actually it's not it, but it's the Lagrange circle of that thing, which is S1 times S1. So it's in some sort of mapping torus. So you see it's pretty concrete, right? Maybe you can write it down like that. So in order to control the tangent bundle of this W, or at least the part of it which comes from F0 beta, we use the index bundle. And so that's a bundle over the space of maps, just taking maps that are as our homomorphic maps. Right? It's maps from the discrete boundary into L and have homotopy class in this class J beta. And then the tangent bundle of our solution space is actually the restriction of this bundle to the moduli space. So what we are going to do is we're going to try to control this thing in a way piece by piece. So we want to find stable trivializations on the boundary that extends inwards. And that somehow allows a picture, but the first step is to use a sort of linear version of gluing, where we show that you should think about this one piece as a homomorphic piece and the other piece as a flow homomorphic piece. And we want to show that if you have trivialization of the kernel on one piece and the trivialization of the kernel on the other piece, they sort of glue to a trivialization on the joint curve, which is inside the moduli space. So F0. And that's okay, but once we have this gluing set up, then we want to have a notion of the compatible thing. So here somehow this start of the argument is as follows. So we first note that if you have a homotopy sphere, then as a PL manifold, the L, the surrogate thing, is actually homomorphic to the standard one, the circle on the Whitney sphere. And so, since you're in double dimension, they're also isotopic, so you can sort of drag one to the other. But furthermore, if you now look at the tangent maps, so kind of formal, you look at them as formal things, then they are also homotopic, because all in this dimension, all obstruction vanishes. This is just a homotopy problem. And since you can homotopy, you find that the index bundles are actually isomorphic. And so when you look at this index bundle, you can, looking at the index bundle over L is the same as looking at the index bundle over this circular Whitney version. So somehow, in order to prove that this is trivial or something like that, then we need only do it for the Whitney version. And for the Whitney version, this is not very difficult, so we can somehow use our knowledge of the space of such maps, so it's related to the loop space of the sphere, and we have a very standard semi-composition of this loop space, and also if you look at the equation, the D-bar equation, defining the Whitney version, you can somehow explicitly write down solutions and just find the trivialization by hand for the Whitney version, and over the cells of required dimensions. And that now can be exported to that lab. And once you have that, you have a stable trivialization over the piece that came from solutions. Now, over the other piece, you have a similar thing in the direction of the moduli space, also have a stable trivialization. And then you have to study the field. There is a torus that is field. But to extend the trivialization of this torus is just a matter of spin structure, so you can somehow prove that this obstruction can be overcome. So at the end of the day, you now produce this W, which has which is stable periodizable, and so now it might do the job because we have the boundary of this manifold as L rather than our original K, but we can somehow add a two-handed cancelling what we did from the beginning. We get that. So in this way, we somehow give this. So
Do you have any idea if this extra boundary, I don't know where it is, do you have bubbles that show up?
Yes.
Do you have any idea how to bound the number of components?
Absolutely. And I think there is no kind of way of doing that. I mean,
We should re-ask the question. Sorry, can you re-ask the question?
yeah, sorry. So the question was, so if I go back, so the question was about the number of boundary components. So basically, how many components does this space have? So there's a bunch of circles, and a priori you can say it's compact, but I mean, but so it's a finite number, but you cannot say much more than that. And in fact, it's possible that you could choose this Lagrangian so that you have just very few. But if I'm allowed to design the Lagrangian and the complex functions, I would imagine I could get anything.
Do you know what it is for the standard one?
For the standard one. For the standard one, I don't know if it's with some sort of standard Hamiltonian. But
If we did the parallel logic without doing surgery, then we would know it's connected to the one.
yeah, the parallel argument without surgery is a little bit same. But no, well, not that component. You could still distinguish. No, no, I don't know.
I'm only asking you the question because Yasha asked me
Cool.
when or the other.
So, we don't have it immersed exotic sphere. We have a lower bound on the number of critical points.
So it seems like you can immerse them with 3 levels. But this would come from this sort of extension of Murphy's H principle to Lagrangians with loose negative ends. But I'm slightly confused about this. I'm not sure, but it shouldn't be much larger than. It's a little bit strange thing that if you have this one, it's very rigid, but as long as you deviate a little bit from it, you completely lose from this thing. But it's not really well understood. But it seems maybe it's just 3.
Any other questions? Let's take the next step.